All right, we're gonna go ahead and get started. I guess I'll start with the conduct of the exam. The exam opens up Sunday morning at, as the clock strikes midnight. So Saturday, late Saturday night, early Sunday morning. It'll be open until 11:59 on Monday. You need to be done with the exam by 11:59. The exam, there's no place to enter any answers. You're given questions and you have to write down your answers on separate pieces of paper. And then when the exam is done, you'll leave the quiz. Actually, let me double check that. It'll say in the instructions, but you'll either leave the quiz and then scan your answers and upload them, or you'll scan them with the webcam still on you. But I'm almost positive that you leave the quiz. Leave the quiz module, and then you'll scan it and then you upload it into the midterm answer submissions. You have 15 minutes from the time you leave the quiz to when you upload your exam, the timestamp on your upload. So, and Dr. Wayne will look at that and compare it. And if it's more than 15 minutes, then you're going to be in a conundrum, I guess. But that's that. I think you have about 2 hours to do it. Sorry that I'm not all that prepared. I got stuck at work late, but if you can do the midterm, if you can do the practice midterm, well, then you'll do fine on the actual midterm. So if you haven't done the practice midterm yet, or if you have done it and you had to keep going back to homework problems or notes, or even your cheat sheet, then I would suggest just do that practice exam a couple more times. And if you have to look at your cheat sheet once or twice, that's fine, but you should not get in the habit of constantly referring to your cheat sheet during exams, because it'll just, some of the exams that you'll have, not maybe in this course, I really don't remember how pressed for time I was when I took it, but in other courses, if you have to keep going back to your cheat sheet, you're gonna run on it. You're gonna be short on time, and before you know it, you'll be out of your exam. So, and when it comes to the cheat sheet, you're allowed to have anything you want on that cheat sheet. So it's one piece of paper. It's front and back. One normal 8.5 by 11 piece of paper, front and back. It can be printed or it can be handwritten. If for some unsolicited advice, I always find it most helpful to handwrite things. It helps you. I mean, there's been studies done that show that if you write something down by hand, then you're more likely to remember it. So that's always good. So you can have, like I said, you can put anything on there you want. You will be given tables. I believe it's tables 3.1. Let me double check. Tables 3.1 and 3.2 will be available in the exam. So you do not have to write down anything from tables 3.2 or 3.1 on your cheat sheet. If you want to put a whole entire homework problem on your cheat sheet, you can do that. Some of the more confusing things, like how to prove time and variance or something like that, you can put a whole worked out problem on your cheat sheet if you can fit it on there. Pictures, homework problems, formulas, whatever you want on there. Like I said, front and back, you'll have to show that to the camera, and then you'll show all your blank scrap pieces when you're doing your room scan. And if you haven't done the practice exam, not the practice midterm PDF that she put out, but the honor lock practice exam, I'd suggest go ahead and doing that, even if you've done it before. I still, I'll be graduating next or in the fall or spring or something like that. But every time I take an exam, if they offer the practice exam just to do the walkthrough, I still take it, just because that way when it comes game day, you're ready. As that's all I have to say about how the exam will be conducted. Do you have any questions about that? All right. Okay, and what we're gonna do for this practice midterm, or not for the practice, for the midterm review, is I'm kind of just gonna go over some things that kind of get brushed by very quickly in this course, like how to manipulate, how to work with complex exponentials and go between polar form and rectangular coordinates. We'll talk about unit step, unit impulse, some of the more basic things, but it's to me, it's a lot of the things that kind of get brushed over. And then once we get through with that, if we have, if there's any specific questions about the practice midterm, then we'll go over those. Okay, so somebody else just joined us. Chris, I just went over the conduct of the exam, like how it's gonna be taken and everything like that. So if you have any questions about that and we have time at the end, you can go ahead and ask. But we're gonna get into actually some signals and systems stuff now. So let me share my screen. Before I get started, is there can you do that with a calculator? Do what? Patrick, can you do what with a calculator? Yeah, you can. Yeah, you can. You use whatever calculator you want, and it's fine to have it in polar form. But we're still going to go over it. It's and you know I I use a calculator. Stupid not to use a calculator, but a lot of times too, it's good to still go through problems and make sure that you are proficient in, you know, definitely single integrals, probably some double integrals. Actually, definitely some double integrals. If you haven't taken triple E 350 yet, you'll have double integrals in that class. When you get into triple E 241, which is electromagnetics, that class is pretty much entirely that whole class is it's a semester of vector calculus applied to electromagnetics. So it's always good to stay proficient with your algebra, your complex arithmetic, and your basic calculus and linear algebra, because those are just going to be that's the degree plan we're in, and all that's necessary in just about every class that you're going to take. You're going to be dealing with complex exponentials, differential calculus, integral calculus, and once you start hitting your 400 level calculuses there, or 400 level classes, there's going to be a lot of matrix algebra or matrix math in that. So it's good to just stay current with that and sometimes work it out by hand. But when it comes, exam time, I do everything on a calculator too. So, but yeah, you can use whatever calculator you want. There's no requirement. I have the TI, what is it? The Nspire with the algebra system. So it's a handy thing to have. Let me, I don't know where my chat went. Okay. All right. Can you guys all see my little, my OneNote screen? Yeah, the CAS. That's the one I have, Patrick. Okay. So first we're just going to run through some basic complex arithmetic, and the terminology that's typically used when they talk about it is they'll say we have a complex number and we call it S, and it has a real part, which is typically denoted as sigma, and an imaginary part, which is denoted as omega. So if I wanted to refer to the imaginary part, or if I wanted to refer to the real part of S, I would just write sigma. And if I wanted to refer to just the imaginary part of S, I would just write omega, not j omega, just omega. The j's, kind of implied, and that's what gives it that. That's what makes it the imaginary part, because j is the imaginary unit. And just as a reminder, the square root of -1 equals j. And that's the rectangular form. Now let's get a plot up here. And now we're going to be on what's called the S-plane. And this is your imaginary axis, so your j omega, and then over here is your sigma. And complex number is pretty much just like working with a two-dimensional vector. If you had a vector, just say r, and it equals we'll say alpha times I hat plus beta times j hat. It kind of works the same way as this. So let's define a complex number S naught, and we'll call it sigma naught plus j omega naught. And we could say that sigma naught is right here, and j omega naught is right here, or omega naught, excuse me. And we put this point in the plane, and then we can draw an arrow, call it a phasor or a vector, whatever you want to call it. It's more of a phasor, or it is a phasor. It's not a vector, but Same principle. And so we could describe this phasor using rectangular coordinates as we've done right here, or we could describe it using polar coordinates. Now, on a 2D plane, if we want to describe something in polar coordinates, then we need an angle from the origin and we need a magnitude. So that would be the magnitude of S naught, and then we'll call this angle theta naught. So the magnitude of S naught is given by the real part squared plus the imaginary part squared, and take the square root. Now, once again, I said the imaginary part. We did not include the J right here. If we had done that, and this is bad, so all right, I'll preface this. If we had done that and we did sigma naught squared plus J omega naught, that whole quantity squared, then what we're gonna get, and here's let's just go up here real quick. If I square this whole thing, then I'm gonna get -1 is equal to J squared. So if I do this, the bad one, then we'll get, we could separate it, but I'm not gonna do it. But essentially you square that J, turns into a minus, and then we'll have omega naught squared. And these are not equal. So when you take the magnitude, you drop the J, and you square both things, and you square both parts and you add them, okay? And if we, and then, so that gives us one quantity in polar, right? Now we want to figure out how do we get this theta? Well, if we look at this, let me get this a little bigger. It's kind of tight. Not that big. So here's our phasor. Now this angle right here, theta, the opposite side of that angle would be, this is omega naught right here, and the adjacent side right here is sigma naught. So if we want to know what theta is, then we take theta naught, and that's going to be equal to the inverse tangent of the opposite, which is omega naught, over the real part, which is sigma naught. And a handy way to remember this, but you have to be careful because it has to be in a certain quadrant, and I'll get into that in a moment, is that it is the inverse tangent of the imaginary part over the real part. And that gives you theta. So that's how you go back and forth between your polar and your rectangular. And let's discuss something else real quick. So another way that we could, and I'm sure some of you might be familiar with the notation. It's something like this. This is kind of called, I'm not sure if this is called polar form. I know it isn't like my calculator, but this is a polar form too, but this isn't one you're going to want to use in this class because this implies that we're dealing with a single frequency. And if you ever take like a power class or something like that, where you're dealing with 60 hertz, then you can do all your stuff like this because everything's 60 hertz, but we're not in a power class. We're in a signal systems class where most of what we're doing is with a variable frequency omega. But so when we have the polar form and we want to write it in polar form, then that's where the complex exponentials come in. So if we take a look at Euler's identity, let's say e to the j omega t, Euler's identity is that e to the j omega t is equal to cosine of omega t plus j sine omega t. And if we took the magnitude of this, e to the j omega t, that's the same as taking the magnitude of this side. And we'll come down here. So we're going to take cosine squared omega t plus sine squared omega t. And this is the fundamental trigonometric identity, and this has a value of 1. So anytime you see a complex exponential written like this, and there's no coefficient out front, then that means that this complex exponential has a magnitude of 1, or what we call unity magnitude. And I'm going to say that again. Anytime you see a complex exponential written like that and there's no coefficient up front, then that has a magnitude of 1. Does everybody understand where I'm at so far? Just, I'll assume yes, unless I hear it or see a no. So if we do have a complex number S naught, then we can represent it as such. And this gives us, this is equivalent, this is equivalent to sigma naught plus j omega naught. Same thing, just different ways to write it. Addition and subtraction is easier in this form. Multiplication and division is much easier in this form. And you know, if you're using your calculator, just go ahead and use your calculator. But that's just some basic stuff. Let's go over some angle stuff real quick, just because sometimes it gets confusing, but I don't think there's really too much to worry about in this class when it comes to the angle. But if we had a different, let's say S naught came, so here's our angle for this one. This is theta naught, and it has magnitude S naught. If we applied the same formula right here, taking the inverse tangent of the imaginary part over the real part, well, you can see here that if we're talking about the imaginary part over the real part, then what we're going to get right here is this is our imaginary part, omega naught, and this is our real part, negative sigma naught. So one trigonometric identity is that the inverse tangent of, let's say, negative x is going to be equal to negative the negative tangent or inverse tangent of x. And that's not going to give us the correct number here. So you do have to pay attention a little bit when you're working with your angles and what quadrant there is. But what we can see here is that, let's say we have this angle right here, and this angle is phi sub naught. Well, we know that the angle phi sub naught is going to follow the same rule here of our inverse tangent of the imaginary part over the real part. So then theta naught is going to be equal to pi radians or 180 degrees, whatever you want to call it, minus the inverse tangent of the imaginary part over the real part. Does everybody, does that make sense to everybody? And if we had, let's say we had another one, let's say we'll come down, we'll call this we'll call it omega sub 1. Oh, too long there. Where am I? That's close enough. So now let's get rid of all this. And we'll just call it omega sub naught. So now our angle is coming all the way around here. And when we look at this, we can see that at the opposite side of this angle, this, and then we have another smaller angle right here. We'll call this one again, will be theta naught, and this smaller one here will be phi sub naught. We can see that the angle of phi sub naught is the imaginary, is the inverse tangent of the opposite over the adjacent, or the inverse tangent of the imaginary over the real. So then what you would just have to do for that one is that you would add pi plus the inverse tangent of, what did they say, omega naught over sigma naught. And then when you get into the fourth quadrant, which is over here, we'll put sigma naught right here, and we come down and we're somewhere around here. Now we have this angle here, and this is our, or when we could come all the way around like that and get our theta, or what you could just do is take the negative angle. So you would say, you know, this angle right here is going to be, if this is, I'm using theta right there, so let's call it phi sub naught. Then this angle right here, phi sub naught, is going to equal the negative inverse tangent of the imaginary part, omega naught, over the real part, sigma naught. And I think that's about all I got for the complex numbers as of right now. I got actually one more thing I can show you. Does everybody understand the angles condition right there? It's like I said, I don't think that's going to be a huge thing in this class, but if you take any other signals and systems class or control systems class, you're going to have to know how to play with how to get those angles, and you're gonna want to know it very easily. And an easy way that you can actually do it too is if you don't have a complex plane, let's just say you're given a complex number. Let's say it's S and it's equal to let's say it's -3 plus -3 plus J2. You could just draw a little triangle. You can say, all right, well, here's my -3, and here's my J2, or here's, you know, J2's right here. J2 and -3, and so here's where it goes. So then you can just look at that, draw your little triangle, and figure out, okay, that's right. I need to subtract this angle right here from pi, and that's a handy way to do it, is just draw little triangles. But does everybody understand? I hope everybody's. I don't have any questions, so I'm going to assume everybody does. But that's some basic complex arithmetic and how to go back and forth between those two forms. Now let's think if we just had, let's say we had a number, a complex number. Let's say S sub naught is equal to 1 plus 0 times J. So our number just comes out to, or our phasor just comes out right here. All right. Now this is a complex number. Its imaginary part is just 0, and like I said, you're going to be dealing with complex numbers in pretty much every class after this. So just get used to dealing with them. They're not going away. If I took S naught and I multiplied it by J, then I would get J times 1, and that's going to be equal to J, correct? So when I have now that I've had S naught and I multiplied that by J, so this was just S naught equals 1, and I went up about here. When I multiply by J, so this is J times S naught. When I multiply by J, I have caused a rotation of 90 degrees in the positive angular direction. And recall that the positive angular direction is always counterclockwise, positive theta. And if I multiplied S naught by J squared, and I'm going to drop all that extra math, then we have J squared times 1, and that's equal to -1 times 1, which is equal to -1. So now I'm over here. So this is S naught times J squared. So if I multiply some complex number by J squared, then I have caused a rotation of 180 degrees in the complex plane. So I think you guys are getting the point now that if I multiplied this number by J, then now I'm down here. And if I multiply it by J again, then I'm back to the origin. So every time you multiply by a J, that's just a shift, or not a shift. That's an angular rotation of 90 degrees in the complex plane of wherever your phasor is. So if your phasor is here and you multiply by J, then your phasor is going to be over here, and you'll have a right angle right here. I just had something in my head that I wanted to bring up, but I can't remember what it was. Oh yeah. So a lot of times, and I seem to get this question almost every semester, is that there'll be some in some practice problem, there'll be something written like this. It'll be 1 over j. And then the next step is that, then the next line, it's written as e to the minus j pi over 2. And a lot of times people ask me, how did this go from that? So let's go through that. If we have 1 over j, that's actually equal to negative j. That's you can prove that yourself if you like. It's like I said, if you multiply by j, then you cause a positive angular rotation of 90 degrees. So it would make sense that if you do the inverse operation of multiplication, which is division, then you're going to cause a negative rotation of 90 degrees. But anyway, so we have 1 over j is equal to negative j. So if we draw negative j on the complex plane, that would be this one right here. Let's get rid of these on my messy plane. This one right here, that's negative j. Now we can see that negative j has an angle right here of theta, and it's of theta, and theta is going in the negative angular direction, and it's right down the ordinate axis, so we know that that's a 90-degree thing, and 90 degrees is equal to pi over 2. So there's a brief explanation of why 1 over j is written as e to the negative j pi over 2. And we could even go a little bit further and throw this into here. So we'll get minus pi over 2 plus j sine negative pi over 2. And a couple identities, cosine of negative x is equal to cosine of x, and sine of negative x is equal to negative sine x. This is an even. This is an odd function. So when I do that, I get that this is equal to cosine of pi over 2, which cosine of pi over 2 is cosine of 90, so that's equal to 0. And then plus j, or excuse me, this negative sign comes out front. So we get negative j sine of pi over 2. The sine of pi over 2 is equal to the sine of 90, and that's equal to 1. And then we can just drop that 0, and we get that as negative j, which goes right back into what over here. That's all connected. So I think I'm about done with my spiel on complex numbers, unless anybody else has anything they want to discuss about that. I don't mind. I actually like talking about complex numbers. I like trigonometry, and so if you do have questions, please feel free to ask. And if I don't hear any, I'm just going to move on. And we'll just do one more quick thing here. I'm sure everybody knows this by now, but if I had e to the j theta 1 times e to the j theta 2, then that's going to equal e to the j theta 1 plus theta 2. So that's just another simple one. And we can write 0. Speaking of that, we could get really fancy with why isn't this deleted? If we wanted to be really fancy, not 0. If say we had the number 1 and we wanted to be fancy, well, we could write it as e to the j 0, because any number raised to the power 0, because that's just going to be equal to e to the 0. Any number raised to the 0th power is equal to 1. And if I wanted to, I could actually go a little further, a little more fancy with this. I could write, well, that's e to the j pi over 2 times e to the negative j pi over 2. So I know there's a homework problem in week 3 that again, it's pretty much every time every term there's a class. I get multiple questions. How come I can't make this answer look like the back of the book? And it's because, well, you have to use this little fancy way here to write 1 and separate your exponential to the 0th power into an 2 exponentials being multiplied by each other, 1 to a positive power, 1 to a negative power, and then you could factor that out. So if I did have something like, let's say I had 1 plus e to the j negative j, we'll say j pi, then I could write that as e to the j pi over 2 times e to the negative j pi over 2 plus e to the negative j pi over 2 times e to the negative j pi over 2. Keep working that. I'm going to factor out an e to the negative j pi over 2, e to the negative j pi over 2. And then I'll put this in here, e to the j pi over 2 plus e to the negative j pi over 2. And recall that 2 cosine of x is equal to e to the j x plus e to the negative j x. So if I divide 2 by both sides, if I divided 2 by both sides, I get that cosine of x is equal to 1 over 2 e to the jx plus e to the negative jx. And I can make this and this look the same by multiplying by 2 and dividing by 2. Then I'm going to get I'll get 2e to the negative j pi over 2. And then I'd have e to the j pi over 2 plus e to the negative j pi over 2 all over 2. And that's going to be equal to 2. We could actually write it as such, going back to what we just did, negative j times 2 times cosine of pi over 2. So that's how you can go, from a complex number like this, where you have a sum of this is a purely real number plus a complex exponential, and go into complex, a sinusoid with a imaginary magnitude. But any questions on that? Does anybody have, before I get started on just kind of pulling another topic out that I feel is breezed through quickly in this course, and I'm going to write one more identity real quick just so we can see something. Let's say we had e to the j omega t minus e to the j omega t, e to the j omega t minus e to the negative j omega t, and we write that out, then we will have, we'll have cosine of omega t plus j sine of omega t, and then minus cosine of negative omega t plus j times the sine of negative omega t. Applying a couple of those trig identities, and then we'll get cosine of omega t plus j sine omega t. Recall that the cosine of negative x is equal to the cosine of x, so we just get omega t right here. And then this minus sign is going to come up front. It'll come up front and it'll multiply all the way over to here. So this turns into a plus sign, plus j sine omega t. This cosine and that cosine cancel, so we get e to the j omega t minus e to the negative j omega t is equal to 2 times j sine omega t. These are handy to know and to be able. It's not hard to show this to yourself. If you've never just actually written a complex exponential and then applied Euler's formula, I'd suggest doing it because it gives you a little more intuitive feel to it. And if we had something like if omega t was equal to if omega t was equal to 45 degrees, then we're going to end up with an actual, this will actually end up turning into a number. If omega t equals pi over 4, then 2j sine pi over 4, that should be equal to what? That's 2 times j over the square root of 2. So, which and most time in this class we're gonna always have this complex, omega, this variable omega there, but in a lot of other classes, sometimes you'll get a complex exponential. I'll say e to j 60 degrees, and when you see that, when you see this, you should be thinking, all right, well, I have something in the complex plane like this. It has a magnitude of 1, and this angle right here is 60. And if this angle is 60 degrees here, then I know what this magnitude is here. If I know the magnitude as well, we said it was 1. But if I know the magnitude is 1, and I know this angle is 60 degrees, and I know how large my real part is, and I also know how large my imaginary part is. And like I said, I'm not gonna say to be successful. I've found it very handy that I'm good with complex numbers, because you can get, if you're not, and I'm sure it's happened to some of you guys, if you're doing homework or you're doing an exam and you get hung up on something that's just simple, you think it's it's just something you haven't done in a while. It can kind of put a damper on a day, wasting a couple hours trying to figure it out, when it's just something that you did know intimately at one point, but because you haven't practiced it lately, it's kind of not there, not on the tip of your tongue. So that's all I have for complex numbers now. Does anybody have any questions about complex numbers? Did everybody understand that? Either type or say yes, please. Awesome. Got enough of you guys. All right. Now let's go over. Let's before I start picking other topics. Is there anything anybody would like to go over? The next thing I was going to go over was the you want to go over CT convolution? Okay. The next thing I was going to go over real quick is the sampling, or not the sampling. The sampling property and the sifting property, and then I guess that'll lead in a CT convolution pretty well, I think. So we'll start there then. And I'm going to get my formula sheet out just so I don't mess anything up and confuse anybody. All right, the sampling property of the delta function. So we have x of t. My pen's kind of acting funny, so if something happens, and yeah, what's going on here? So we have x of t is equal to, oh no, sorry, x of t times delta of t, which is the unit impulse. That's going to be equal to, man, what is going on with my pen? Sorry, x of t times delta of t is going to be equal to x of 0 times delta of t, and x of t times delta of t naught is going to equal x of t naught times delta of, I should have put a t minus t naught in there. T minus t naught is going to equal x of t naught times delta of t minus t naught. And the reason for this, so let's say we have some signal x looks like this, comes up, goes over, and it just comes down. And we could say that this is the origin right here. And if I have an impulse at the origin, that's the only place where the unit impulse, if we're talking delta of t, that's going to be equal to 0 if t does not equal 0, and 1 if t equals 0. So if I multiply some signal x, where x is this squiggly little box here, I multiply that by the delta function, or the unit impulse, or the delta function, whatever you want to call it, then all that's going to happen is I've sampled the value of x at the origin, and we leave this delta function on this side, because if I didn't, then what I would be saying is that essentially whatever this value, say x right here was equal to 1.2. If I say that x of t times delta of t is equal to x of 0, then, and I wrote this out as a piecewise function, I'm essentially saying that it would be equal to, what did I say, 1.2? It's going to be equal to 1.2 up and down the imaginary axis. So, or up and down the time axis that we're on right here. So that's why that delta of t is there, because that delta of t, when we put that delta of t there and we write that as a piecewise function, then we're going to get that it's equal to x of 0 when t is equal to 0, and it's equal to 0 when t does not equal 0. And I don't think I really need to go over the shift. If I shift it, I'll go over it anyway. If I did shift it, so here's 0, and let's say my x looks like this. And I have an impulse right here at t naught. And I do the same, it all works out the same way. I just do the picture just to kind of help put a little intuition behind it. But you can see that I'm sampling it only at that instant in time. And that's where I get this. And the whole reason we have that delta function there is so that we can write it out as that piecewise function again, except this time we'd have, we'd say t naught there and t naught there and t naught there and change that shit. So, or change that stuff, sorry. Everybody, does that make sense to everybody? All right, so now we're going to get into, so that is, what did I say? That's the sampling property of the delta function. So now we're going to talk about the sifting property, which is convolution with the delta function. And this is probably one of the most, to me, if you understand this kind of concept, then you're going to be sitting well at the end of this course. It's just a fundamental thing. Let me see. Sorry. So x of t convolved with delta of t is going to equal, that's just going to equal x of t. And it doesn't matter if you're talking t's or n's, just so it doesn't, if it's x of n convolved with delta of n, then it's going to equal x of n. But I'm just writing t's. And then the other part of this is that x of t convolved with a time shifted delta function is equal to x of t minus t naught. And if let's think about why this is. Give me a couple axes. Let's do an easily replicable triangle. Here's my delta function. It's at magnitude 1. Call it h, or h is equal to delta t, and then t. So if I convolve these two, this signal with this system, then what I'm doing is I'm essentially passing this signal right here through this system. So I could take it, and if you've watched any videos about it, there's the whole, if we visualize it, so here's that signal. So now what I'm going to do is I'm going to flip it, even though it's supposed to be symmetric, but this signal is going to enter this system like this. So this, we have to remember that this is actually, it's just get right here. And we'll say that this out here is at -2 and this is at 2. So if I started this convolution and I took a snapshot in time at t equals -2, then this is what it's going to look like. My system and my signal are they're about to interact as much. They're about to interact, but they're not interacting yet. It's that kind of that weird, limbo area. But as it comes through, then I multiply my signal times my system and I add it. And that gives me a value at that moment in time. And then as I keep doing that, I multiply and I add, and I multiply and I add, and multiply and I add, and I take the limit of that I take the limit of that shift going to 0, and then it turns into the integral. And all that happens is it's going to recreate that signal, and it's going to recreate that signal right at the origin. And if I had a time shifted delta of t, let's say right here, t minus t, or let's give it a number, let's say 4. Yeah, that's about 4 right there. So if I have a time shifted delta function, that's right here. And I do that same thing. I flipped it and I've shifted it, and then right now, and I put it here. So this is a snapshot in time at t equals 0. This is a snapshot of the convolution at t equals 0, which kind of makes sense that we have no interaction yet. Our signal starts at t equal to -2, and it has a length of 4, but we're not even concerned with it because recall that we flipped it. So this is kind of like the t equals -2 side, because we're talking time. We're not talking just some spatial coordinates. So when we're talking time, we have to start from the earlier time. So it wouldn't make sense that we have a non-zero value if the signal starts at -2 and the system starts at 4. Now, if the signal started at -5, then we're going to have a non-zero value at t equals 0. We'd actually have a non-zero value at t equals -1. And if that confuses, you'll go into more of that in a minute. But when we go back to this convolution, then what happens is, well, here's t equals 2, and then we just start tracing this out again. It's just going to do the same thing that it just did. It's just going to recreate that signal. It's just going to be centered about that impulse. So x of t times delta of t minus 4 is going to be equal to x of t minus 4. And that's just a shift. That's just a time delay. So if here's 0 and 4 is out here, then we just have a signal that kind of looks like that. It's this, same one as that. It's just centered about that impulse. So again, this is the sampling, and this is the sifting or the convolution with a delta function. What do they call it? What you call it on the sheet? The convolution with the delta function, or she calls it parenthetically the sifting property. But in most books, you're probably going to read it as the sifting property. Any questions about the sampling property or the sifting property? And let's go into something real quick. Let's say I'm going to kind of work one of the problems very briefly, but from the midterm. Let's say I'm given and this is h of n. So this is our dt impulse response. And that's what, and actually back to it, that's why we call it an impulse response. Because that impulse response is just, we send that impulse through the system, and the impulse response gives us that system because it just traces out the signal at wherever it was. That sounded a little ambiguous, I'm sorry. But anyway, let's say we had some signal and it looked like this. And we'll come, let's go right here. And this has magnitude 1, this has magnitude 2, this has magnitude 3. Here's -1, here's 0, and here's 1. So here's a graphical depiction of h of n, and now we can define it. We could define it in terms of unit steps. We could say this would be u of n minus, or n plus 1 plus u of n, just u of n, and then plus u of n minus 1, right? Because this is going to turn on, this will turn on at -1. This is on at 0, and then this is on at 1. Or what we could do is define it in terms of delta functions. So we have a delta of n plus 1 plus a delta, or excuse me, plus 2 delta n plus 3 delta of n minus 1. And if I had some arbitrary signal x of n, and I want to know what's the convolution of x of n and h of n, well, then that's going to be x of n convolve with delta of n plus 1 plus 2 delta n plus 3 delta of n minus 1. And recall that convolution is distributive. So then we could rewrite this as x of n convolve with delta of n plus 1 plus x of n convolve with 2 delta of n plus x of n convolve with 3 delta of n minus 1. And give myself a little room here. And now we just get to apply the shifting property. So this is x of n plus 1. So when this one, all it did is it recreated my signal x, and it just did it centered around -1. And then we have a constant coefficient here, so we get to pull that out because convolution is linear. So we have 2x of n. And then down here we have another constant coefficient, so we pull that out. So we get 3x of n, and we evaluate it at where the delta function is. So that's n minus 1. And I honestly think that when it comes to a DT convolution, this is probably the easiest way to do it. You're not going to be given, especially on exam. I know in that convolution homework, there was like a signal there. It went up to like 20 or something like that. You're not gonna get anything like that on exam. If you get a DT convolution, then you're probably gonna have 3 or 4 impulses in your system and your signal each. Which so you have anywhere. Let's say you had 2 and 2, then you'll end up with 4 impulses. If you had 4 and 4, then you'd be out there. You'd end up with 3 actually. But if you had 4, then you'd 4 in each, then you'd end up with 7. And a handy little trick that if we have y of n is equal to the convolution of x of n and h of n, then the length of y of n is going to be equal to the length of x of n plus the length of y of n, oh, sorry, not y of n, h of n minus 1. So this is something you can put on your formula sheet if you wanted to, and you could check your convolution signal to see if it is the correct length. And if you're having trouble with a CT convolution, then what you could do is you could sample your signal at a couple spots just to get an idea of what it looks like. So if you had 2 continuous signals, or a continuous signal and a continuous system, and it was fairly small, if it's a sine wave or something like that, if you had something like this, and you just wanted to get an idea, well, what's this look like after it's been convolved with my system, you could actually take a couple samples, I'd space them out evenly just to make it simple. And you do this to both your signal and your system. You take a quick sampling of it using impulses, and then you could apply the sampling property, or you could do the graphing method, which is pretty easy with the DT signals, and they'll give you an idea of, well, here's what my shape's supposed to look like. Here's the shape of my convolved signal. This is what it should look like. Here's where it starts. Here's where it ends. That's a handy trick. I think that actually, I can't say it's a handy trick because I've never done it. I just kind of thought about it. But I think it'd be a handy trick. It makes sense to be a handy trick anyway. But so yeah, Do I have any questions about the sifting property or convolving a DT signal? Convolving a DT signal in a system. All right. So let's go over some CT convolution now. And I'll preface this by saying that you're really not going to have to do a whole lot of convolution after the midterm. After the midterm, we just started last week. We learned about Fourier series, and then this week or the next module, no, it's this week is the Fourier series, and the next week will be the Fourier transform. After that, it's going to be DT Fourier transform. Then it's going to be Laplace transforms, and then it's going to be Z transforms. And each one of those kinds of builds off each other. I think by now you kind of see where your differences are going to be between CT and DT. But a Laplace transform is an extension of a Fourier transform, and a Z transform is an extension of a discrete Fourier transform. And before I get into the CT convolution, let me kind of give a little spiel about Fourier transforms and Laplace transforms and stuff. So in circuits 1, which I'm sure most of you have taken, towards the end of that class, you started working with things called transfer functions. So you'd have something like V out of j omega over V in of j omega. And we call this a transfer function. When we take, and if I remember correctly, actually in the textbook, when it first introduced the transfer function, it was using the complex variable S. So it's the output divided by the input, where both of them are functions of the complex variable S. And then it would say, let S equal j omega. Then we get V out of j omega divided by V in of j omega. So we put some signal in, and then we, if we can put a signal in and then measure our output, then we can define our transfer function, right? And then you would start working with things called Bode plots or Bode plots, and it would look like something like this. Here would be the magnitude. This would be the magnitude of V out divided by V in, and then this was either omega or just a normal time frequency F. But you have Bode plots, and they'd look, you might have like a low pass filter, or you could have something else, a high pass filter, something that come up like this and go like that. But long story short, this is the frequency response of that transfer function in the steady state. So I apply a input. Let's say I applied a constant sinusoid. Then, depending on what my frequency of that sinusoid is, going to tell me how attenuated or how amplified my signal is going to be. And when we're talking about Fourier transforms or the J, anything with a j omega, then we're discussing the steady state of the system. Laplace transforms are used when we want to talk about the transients of the system as well. So if we have a Laplace, if we had y of s is equal to h of s times x of s, and then we took the inverse Laplace transform of y of s, we could get something that looks like, it could look like e to the negative j alpha plus some sinusoid omega t. And this would be a t up there as well. Laplace transforms are going to give us the information about the transient response of the system. And then if we let t go to infinity, then this is going to go away. And then we have this. And then we're back in the Fourier domain, because this is going to be our steady state. And when we say steady state, that's what we mean. Say, well, what happens as t goes to infinity? Well, if we have any exponential decays, if we have any transients, those will decay away, and then here's what we're left with in our steady state. And you could think about it as the cruise control in your car, right? So you set it at 55 degrees, and then you start going up a hill, and you can consider that kind of like a transient. And then once your car has the time to respond, and if as long as the hill is constant and has a constant slope, when it has time to respond, it's going to reach back to that speed that you set it at. That's its steady state. So that's an example of a very poor example of a transient decaying away. And then when it comes to the Z transform, like I said, the Z transform. So in CT, this is CT. We have Laplace transforms, and then in DT we have Z transforms. And in the steady state in the Fourier analysis, then we write that as y of j omega and y of e to the j omega. And the reason we write the e to the j omega is so that way we can kind of, it's just a notation to let us know that we are working with DT signal. But that's where this class is going. And one nice thing is that if we do have some y of s, and this is how it's defined as the multiplication of the Fourier or the Laplace transform of the system impulse response times the Laplace transform of the signal, then the inverse Laplace transform of y of s is going to be equal to h convolved with x. And if we can just take some Fourier transforms or Laplace transforms and then just do some multiplication, then what do we need convolution for? And it's also a lot easier to work in the frequency domain with in a lot of respects, and a lot of the stuff that you're going to do in some of your other classes, it's much easier just to do analysis in the frequency domain than it is in the time domain. So you're probably going to go to the frequency domain anyway. So why do the convolution here when I can just multiply my stuff up here? So after this midterm, there's not going to be too much convolution. There might, and I'm not saying this as a fact, I'm just saying there could possibly be a question about it on the final, but the final kind of deals more with the second half of the course. But you're going to need to know material from the first half of the course as well. But there's my little spiel about where the class is headed. I meant to lead off with that. Does anybody have any questions about that? Does anybody have any questions about why we take this course? No? Okay. All right. So a CT convolution. Did you watch the videos? Is there anything like, Patrick, that can you give me a little more direction on what you want help with? It's okay to talk, man, too.
No, I didn't. I had Circuits 2 is driving me crazy. So I didn't have time to watch the videos. I'm trying to catch up there.
Okay.
I just know that I had the most trouble in the homework with the convolution and continuous time. And I just wanted to see that you worked one, and then.
Okay. I'll go through one. I'll go through one a little bit briefly, but I'm not going to do one in its entirety. There's multiple videos up there about it. So
Okay.
if you watch them and you still have questions, then dude, I'll answer whatever you want. But
Gotcha.
But we can go talk about it a little bit though. So let's do a triangle. Nice easy shape. Oh, that's why it's not in the origin. No, it's not in the center of the box. I'll take some circuits 2 questions too. I like that course. All right, so there's our triangle. We can say that this is X, and let's get us another thing. And here is H. And we'll make H, what do we want to make H? We'll make an exponential that cuts off right here. Here's 0, 1, 2, and this is 2. Here's 0, and here's 2, and then we get T, and we get T. All right, so the difficult, yeah, the labs in that class, that is, you're 100% right about that. The labs in that class they do take forever, but it's interesting. But it does, yeah. And over the summer too, I can imagine that's a bitch. So I think in one of the videos I have, I think actually in any CT convolution video I had, and I know there's one DT1, I do the graphing method. And essentially what the graphing method is we're in the time domain right now. So let's define something real quick. That equals x of t. I'm going to drop my t's. I'm just going to write it, and that's equal to, what's the formula for this? It should be negative infinity and to infinity, and then it's x of tau, h of t minus tau, d tau. If somebody could confirm that, that'd be nice. Or we could write it as negative infinity, h of tau, x of t minus tau, d tau. So before we get started, let's look at this real quick. We have an integral, right, over all of time, and we are integrating with respect to tau. So when we're done with this integration, we will not have any taus. Now we do have this t in here, right? And let's remember that what we're trying to get is that we're trying to get y of t. We're trying to represent our output signal y as a function, thank you, Patrick, as a function of time. So it would make sense that we probably end up with a t in whatever results from this integral. We don't want any taus, but we like a t. So that means, and in order to have a t, let's just say we had an integral like this. Let's say it's 5 tau d tau. If we integrate this, we're not going to get any t's. There will be no t left in this, or let's make it really simple. Let's do 5 times d tau. Well, that equals 5 times tau, 4, 0, that equals 20, right? But when we have two continuous signals, we're probably not going to end up with a y of t equal to some constant. We want it essentially to be a function. We want y to be a function of t. I don't like using the word y as a function of t in this class because we're dealing with signals and systems now and not really pure mathematics. So when we start talking about something as a function of something else, people get a little confused because they'll ask, well, why is an x a function of y? But that's sidetracking. But we could, if we change that for out, we set this upper bound to 5, then what's going to happen? And let's just put this one down here so that we actually have a number. We'll have t and we'll have 2. And that's going to give us 5t minus 10. So if this was y of t, now we have y as a function of time, like we kind of desired. And I'm going to change this real quick. I'm going to make it so that way we can go a little bit negative. All right, so here's our new h. So doing the graphing method, let me get some lines out here. Should be able to squeeze another one here. And let's take this guy. Let's bring it down here. All right. So actually, I'm gonna come up here. First things first, let's get some solid definitions for our signal. So x of t is going to equal, man, I gotta do some math. What's that? That's gonna be, if this is 1, then x of t is going to equal, that would be 1/2, because it goes, this is, no, it would just be t. And then if I extended that, then that's going to be 2, and then it'd be 2 minus t. And this one here is for 0 less than 1. Oh, excuse me, 0 less than t less than 1. And this one here is 1 less than, let's put some pure bounds in there with t less than 2. And then our h is equal to, and it says magnitude 2, so it's equal, and what's right up here, we'll write 0 else. And h is going to be equal to 2 when -2 is less than or equal to, let's put less than or equal to t less than or equal to 2, and then 0 else. And looking at our formula here, we have x of t minus tau. So and we're integrating with respect to tau. So let me hold on, give me 1 second. Let me grab this little book, because he writes it in this book well, and that way I don't butcher his words. Well, he doesn't actually say what I was trying to say. Anyway, we know we're integrating with t, and we're gonna be on these tau axes, okay? And we're gonna flip, and as a little hint, I always think it's easier to flip the signal if you're dealing with one signal that crosses the t equals 0 point, and you have another signal that starts at t equals 0. I always find it easier to flip the signal that starts at t equals 0. So let's put a 0 right here. We'll put a 0 here, and then a 0 here, and a 0 here. My little scroll bar. I don't know how to use OneNote. And this one right here, this is going to be h of tau, and h of tau is going to look the same, so it's going to come out to -2 and 1 and 2, and it comes up to 2, just like that. And let's now flip x of so this is x of t up here. So we're gonna flip it, and we're gonna put it on the tau axis. So now we're gonna want, let's write, and I'm actually gonna write it down here. Do it on this third one down. This is going to be x of -tau, and it looks 1, 2, it looks like this. All right. Excuse me. And if we're looking at our pictures, well, we can already see that we have interactions here, right? And it would make sense that, like I was talking about earlier, if we are talking about a convolution right now, just looking at what our signals looked like on the tau axis and with x flipped, and a snapshot. This is a snapshot in time at t equals 0. And eventually we'll get here, but this will be a snapshot in time at t equals -1, and this one will be a snapshot of time at t equals -2. And because in our definition of convolution, we just have h of tau, there's not going to be any shifting of this signal. The only signal that's going to be shifting around is the one that has the t minus tau. And if we did write x of, let me get some stuff over here so we can actually be a little more clear. H of tau, this would be x of, who is texting me? Sorry, -2 minus tau. And this one will be x of -1 minus tau. And then this one right here is x of 0 minus tau. And let's write x of -2 minus tau. We could rewrite it just for the sake of clarity, like that. So then we're gonna be, here's 2. So here, nope, I want to be further than that, don't I? I want to be over here. Start here, come to here, and go to here. So I flipped my signal, and like I said, it doesn't matter which one. Pick one to flip. Doesn't matter which one, because I had that written earlier that x convolve with h is equal to h convolve with x. It's that's commutative. That's the commutative property. Convolution is commutative. Once I flip that signal, then I'm going to shift, and this might sound weird, but I'm going to shift right by whatever t I want to take that snapshot at. Now, I shifted right in this top one right here by -2. So if I shift right by -2, I am shifting left by 2. And now we can see that, well, it's going to be at t equals -2 where I start getting non-zero values, right? So where I start getting non-zero values. So we will have, let's start figuring out some ranges here. We have, or we don't need to do that. We can do y of t equals 0 for t less than -2. Does everybody clearly see why I can make this assumption and not be in any signals and system trouble? Now let's draw another x, and here is a snapshot in time at t equals -1. And remember, we're trying to find y of t. We want to be able to plug in a t and have a y spit out to us. Now we can see that we're having these interactions. So if I start looking at this, all right, so here is at t -2, and I start coming in, and let's say I pause right here at t equals -1. I want to redraw this down here too, just so it's the convolution of this. So this is a snapshot at t equals -1. The convolution, or with the output y of -1, would be equal to the integral, and we just see where we line up. We go from -2. We go from -2 to right here. This is -1 to -1, and it is h of t times x of t minus tau, d tau. Now, h we defined, h is a constant. It's equal to 2. Equal to 2. So -2 to -1, 2 times x of t minus tau. And we really don't even need the definition. We can kind of see what it is just looking at it, but we do have the definition, and it is up here, but well, it's kind of funky because it's backwards. But when we do flip that, how do we write that? Let's write, it would be 2, and then it's times 2 minus t minus tau d tau, and then working it out. Well, what are we gonna get here? We're gonna get 4 minus 2t, and then plus 4 tau. And if I did this integration, then I get y of -1 I get 4 times tau at -1, -2 minus 2t tau -2, -1 plus 4, or no, it'd be that'd be 2 times tau squared at, running out of room. I don't need to go through the integration. You guys know how to do integrals, but essentially when we find that God dang, what is going on? When we're trying to find the convolution right here, we're just essentially multiplying this times that, multiplying here times here, multiplying here times here. We're doing that continuously and then adding it all up. And those deltas, like I said, or those time shifts they go to 0, and that's where it becomes an integral. But let's say I didn't have a time. Let's say I just wanted to know at any value of t. Let me erase my little marks here. And here's where this is the kind of the trickier part of it. But if I pause right here, this is a snapshot at t equals -1/2. This is a snapshot at t equals 1. This is a snapshot at t equals -1/2. And I might have to break my integral up because I'm going to have 2 different values of x. I should have done something that's easier than that. But essentially what happens is, until about here, what's going to happen is I have a changing output, right? So this is at t equals -2. So up until I get to t equals 0 right there, from t equals 0 to t equals 2, I'm going to have the same value of y of t. But if I want to know, well, what is it up until this point right here, then I just change this upper bound. And I'll write that. Let me write this over here. And this is going to be from -2 less than or equal to, or less than t, less than, and what did I say? So here they start interacting at -2, here's -1, here's 0, so to 0. And then over this whole region here until we get to here, so that goes from here we're at t equals 0, and then right here we are going to be at t equals 2. So that whole region right there, because we're dealing with these constant shapes, this one kind of makes it easy. And like I said, there's videos. I kind of picked something just off the top of my head that I can go over quickly because we're running out of time too. But what we're going to have here is y of t is equal to negative. I guess you could actually pick pretty much any range you want. You could do -2 to 0, h of tau, x of t minus tau, d tau. And that's going to be for 0 less than t less than 2. And you'll end up with a t. This when you do this math, you'll have a t. There will be a t sitting there, but it makes sense because y is a function of t. But when you go to plug in, if you plug in t equals 0.1 or t equals 0.2 or t equals 1.9, you're going to get the same output right there. Does that make? I hope that makes sense to everybody. But anyway, that's that part. And then when we start looking at this side here, now we're in this almost final range, and we can see if let's say we bumped it to here, okay, then who's that? Somebody coming in this late? Actually, let me go back to this one. So instead of writing it, because I'm going to try to keep the integrals kind of going. So here's the range that we just went over, right? So let's say we integrate, we're going to integrate it from 0 to +2. And that's just so that way we can kind of have our integrals look like a pattern. But now, when my signal starts leaving my system, right? It doesn't matter really where it's at as long as I'm out here. I'm still going to be integrating. I'm integrating up to that boundary of 2, because this is my area of concern. And my area of concern is this being multiplied with this non-zero value over here. Everything out here is being multiplied by 0. So that's all 0. And what is changing I'm checking something real quick, see if I made a mistake. I don't think I made a mistake, but that's -2. Yeah, I didn't make a mistake. Oh, sorry, I was thinking about the other way. That's this is the reason I like, if you have a signal that starts at 0, to flipping that signal. But when I'm here, what we can see is that the bound that is moving is this backside. Okay, so let's take this one here and we'll shift this here. And this is, we'll put it right here. So this would be a snapshot in time. It was here, and then I moved over 1 and over. So this be a snapshot in time at t = 2. And for this last region, like I said, what's changing is this left-sided bound right here, and that's going to be depending on, well, where are you in time? So if I'm right here, I'm at t = 2, and if I'm over here, then I'm going to be at if I'm at -2, and then -2, 2, that would be 4. I made a mistake. That right there would be, let me go through that one more time. Whoa. -2, -1, 0, 1, 2. And then what's that? That one's at 3. Sorry. This would be t = 3. And then at t = 4, my system, or my signal, has pretty much left my system at that point. That doesn't make sense to me. I made a mistake somewhere up here, because I should have a convolution that is about five units long. Oh, that is about, yeah, no, that's good then. Sorry. Let me motor through that. So here we are at, this is at t = -2. This is at t = -1. This is at t = 0. This is at t = 1. This is at t = 2. Here we're at t = 3. And then here we're at t = 4. And we can write that down actually right now. This is for t > 4. That's that. Oh, I got to give myself the room to write. But let's go back to this example. Sorry, I'm all over the place. We have this backside boundary is the one moving right now, right? So when we perform this next integral, it's going to go from, that would be, the top side is going to be 2, but the bottom side is going to be, if that's 3 and we want to be at 1, then we are going to do t - 2, because this is a snapshot of time at t = 3, right? But we only need to integrate from tau = 1. That's one of the tricky parts about doing the CT convolution. But remember, we're on the tau axis, okay? This is it. So that means our bounds of integration can't contain taus. We want to integrate in this snapshot right here. We want to integrate from tau = 1 to tau = 2. All right, and this is a snapshot of t equals 3. So if tau equals 1, t equals 3, then t minus 2 is equal to tau. And I think I might have made that mistake when I did this one earlier. Give me 1 second here. So this is t equal to -2. And then this is t equal to -1. Tau is equal to -1. T equals -1. Tau equals -1. So in that case, t is equal to tau. All right, I guess I didn't have to fix it on that backside. But and then as we keep moving along, we get to here. Sorry, I didn't finish this. That is 2 less than t less than 4. And then after that, we get 0 for t greater than or equal to 4. And then let's just put some, put that one there, and then we'll put that one there, and then we'll put, I guess just leave that one there. I guess we do this, just make it look simple. But that's kind of the brief thing about CT convolution. Like I said, I got videos where I explained it well, because I kind of like rehearsed before I did it, I guess, or I just kept making videos until I did stutter with myself, because it is a difficult thing to learn. It's probably one of the harder things in this class, probably the hardest thing in the class to learn. And to be honest, like I don't think when I passed the final and I got my A in the class, I probably wasn't that good at convolution, because when I started TAing for this course and somebody asked me, hey, can you help me with this convolution? I was all like, oh yeah, no problem at all. And then I started doing it. And I was like, man, I don't know what I'm doing. I'm going to get back with you. And then it wasn't until I had to teach it a couple of times that I really started getting confident that I could, oh yeah, I can convolve whatever I want now. But it's not something that you're going to use all the time. I make sure I understand it enough to be confident on the test with it. The homework questions, the 2 CT signals that you had on the last homework, and then whatever's in the practice midterm. If you can get good at those 3, then you'll be fine for the midterm. And like I said, there could be something on the final about it, but after the midterm, we're going to be in the frequency domain, and anytime we need to convolve something, we're just going to multiply the Fourier or the Laplace transforms. Watch, Patrick, if you can watch if you have time, please watch the videos, and then if you have questions, just put it on the ed board. You can either do it private or public. We get a lot of private questions. Typically, if you're showing me work for an assignment that's going to be graded, if you're showing me your Cameron or Dr. Wayne work that's for a graded assignment, please make that private. But if it's for a practice problem, or you're not showing graded work, you just kind of like figure out like, I don't understand this about the question, or I saw this in a lab manual. Can you please explain that? Try to keep that public, because somebody else more than likely has the same question as you. It's just a lot of people for some reason are afraid to ask. But Patrick, if you do have any questions, go ahead and ask, and then I'll get on with you. I'll either give you a response, I'll make you a video, or if I need to, I can hop on a Zoom call for like 20 minutes with you to walk you through something. That's kind of all I have for the midterm review. I can entertain some questions for about 10 more minutes. I gotta go, but do I have any questions or anything like that? Comments, or I guess just questions? No? All right, well, like I said, the midterm doesn't open until midnight on Saturday night. So what's that? That's I'm 3 hours ahead, 20. So that's 31 hours from now. You don't post questions about, if you've taken the midterm, then don't post questions about it unless it's private. However, if you haven't taken the midterm and you have a question about midterm review, you can still post that on the ed board. Like I said, as long as nobody's giving anything away about the actual midterm, then you can ask away as much as heart desires, and Cameron and I or Dr. Wang will do whatever we can to answer that to the best of our abilities and make sure that you're confident going into the midterm. And Cameron will be hosting his office hours. I'm on the East Coast. It's 8 o'clock here, 5. So Cameron's office hours will be kicking off in just under 2 hours. If you guys do have more questions or you guys want to get with him about something, Patrick, if you do have a couple minutes, you can watch some of those videos and then hop right on tonight with him. But yeah, if nobody has any questions, then I'm gonna wrap it up here. Yep, no problem, Nathan.
Yeah, thanks a lot. Yeah, I was trying to get through all the homework and I was gonna watch your videos and stuff. Hopefully this weekend before I take the test. So
Yeah,
trying
if you can squeeze it in, because it'll probably help. I think I do a pretty decent job going through all of them, and you know, like I said, if you're still struggling with something, let me